You don't actually understand the Big Bang Theory because what they teach in schools is fundamentally wrong. Most physicists today no longer believe that the Big Bang was the beginning of the universe. The question everyone has about the Big Bang Theory is, what was it that actually banged? Was it a singularity? Nothing. Some kind of cosmic explosion? Let's get to the bottom of this and clear all your beliefs about the Big Bang. Long before modern science existed, humans looked up at the stars and wondered about our place in the universe. There were seemingly infinite descriptions of how the universe came to be. Hundreds of gods with their own creationist stories. The Greek atomists believed the universe was infinite in both space and time, stretching forever in all directions with no beginning and no end. The Hindus, Stoics, and Buddhists all believed the universe went through endless cycles of creation and destruction, birth and death repeating eternally. These ancient philosophies grappled with the same fundamental questions we still ask today. Then in 1687, Isaac Newton published his now famous Principia. In it, he showed that the same laws describing motion here on Earth are true across the universe as a whole. An apple falling from a tree follows the same rules as planets orbiting the sun. Newton's gravity was born, and it was revolutionary. But there was a serious problem with Newton's universe. If his universal law of gravity were true, and every object with mass would attract one another, then surely this force would cause the entire universe to simply collapse in on itself. Everything would be pulled together into one massive clump. Newton borrowed his solution from the ancient Greeks. He basically said that the universe is infinite with no center, so matter wouldn't collapse together because the unseen planets and stars in all directions would balance the entire system perfectly. The gravitational pull from every direction would cancel out, keeping everything stable. Our first scientific model for the universe was born, the static universe. Newton's description of the universe was not only infinite in space, but also infinite in time. It had always existed and would always exist. Newton was a devout Christian and believed that his God may have created the universe, but didn't do so at any specific point in time. The universe simply was and always had been. This idea of the static, eternal universe became widely accepted throughout the scientific community for over 2 centuries. That was until some people realized it had a fundamental problem. When people looked up to the sky at night, they saw bright spots of light coming from stars and large expanses of darkness between them. But if the universe were really infinite and eternal as described by Newton, you should be able to look in any direction and see something. A star, a galaxy, some source of light. With infinite stars in infinite space existing for infinite time, every single line of sight should eventually hit a star. This would make the night sky as bright as the sun itself, blazing with light from every direction. And yet that is not what we see. The night sky is dark. The universe must therefore not be infinite, static, and eternal. Something had to change, something had to give. That change came over 200 years later, and as with many things in physics, it came from Albert Einstein. In 1915, Einstein published his brilliant theory of general relativity, and in it, he made a bold discovery that would revolutionize our understanding of the cosmos. As an observer speeds up, time slows down and length contracts. The closer you get to the speed of light, the slower time ticks for you relative to someone standing still, until at the speed of light itself, if you could somehow reach it, time stops altogether. This wasn't just theoretical speculation, it was a mathematical consequence of the nature of reality. Space and time are innately connected. They are not separate, independent things, but rather 2 aspects of the same entity. They are one and the same thing, forming the very fabric of the universe itself, space-time. Gravity isn't a force pulling between objects like Newton thought. Instead, it's the bending and warping of spacetime itself by objects within it. Massive objects like the sun create curves and dips in the fabric of spacetime. The sun bends the fabric, and the Earth moves around this curved surface in an orbit, like a marble rolling around a bowl. This was all good in theory, revolutionary and elegant, but they needed a way to test it. They needed observational evidence. 4 years later, they got their chance. On May 29, 1919, a total solar eclipse occurred, and it was visible from Brazil. Arthur Eddington organized 2 expeditions on behalf of the Royal Astronomical Society to photograph and image the eclipse. They were doing this specifically to test Einstein's theory. If he were correct, then it wouldn't be just massive objects that move through this bent spacetime, but light itself should be bent and curved to move along this warped path. Light should follow the curves created by gravity. And since during a solar eclipse you can see the stars behind the sun without being blinded by its brightness, they could check and see if he was right. If his theory was wrong and the gravity of the sun doesn't bend the starlight at all, then the stars should appear to be in their normal positions. But they weren't. The stars were shifted from where they should be. They had moved during the eclipse, being warped by the sun's gravity by roughly the same amount as Einstein had predicted in his equations. Einstein was immediately shot into stardom overnight. The Times of London reported with dramatic headlines, "New theory of the universe, Newtonian ideas overthrown." Einstein's name became synonymous with genius itself, and he became the most famous scientist in the world. Einstein's new laws of gravity, didn't just apply to the interaction between objects like planets and stars either. They were universal laws that could be used to examine the fabric of the cosmos itself, the structure and evolution of the entire universe. While he had dethroned Newton with his new theory of gravity, Einstein soon found himself faced with the same problem that Newton had faced 200 years earlier. In general relativity, the universe was fundamentally unstable. It must either expand outward or collapse inward thanks to the force of gravity. It cannot remain static. To try and solve this problem and preserve the static universe he believed in, Einstein modified his own equations, adding in a new value that he called his cosmological constant. It represents the energy of empty space itself. Basically, if you just took a box of empty space with nothing in it, how much energy would be contained in that box? He could then adjust this value to perfectly counteract gravity and match the observations of the static universe everyone believed in. He would later go on to call this modification his biggest mistake, his greatest blunder. But as we'll see later in this story, he might have been right all along. Around the same time that Einstein was figuring all of this relativity stuff out, astronomers had been turning their powerful new telescopes to the night sky, trying to solve one of the longest-standing mysteries in astronomy. For centuries, astronomers had observed these strange fuzzy clouds scattered across the sky. They called them nebulae, with the most famous one being the Andromeda Nebula. They didn't really know what these objects were. Were they clouds of gas within our own galaxy? Something else entirely? The philosopher Immanuel Kant had described them as island universes, separate galaxies beyond our own, but we had no way of measuring how far away they were to test this idea. Distance was the key missing piece of information. That was until a brilliant woman named Henrietta Swan Leavitt made a crucial breakthrough that would change everything. Leavitt was a part of a small group of poorly paid female astronomers known as the Harvard Computers. Despite their critical contributions to astronomy, these women were paid far less than their male colleagues and rarely received credit for their work. Leavitt was tasked with the tedious job of measuring photographic plates to catalogue the position and brightness of thousands of stars. It was painstaking, detailed work that required incredible patience and precision. In doing this careful work, she studied a special kind of star known as a Cepheid variable. These are particularly bright stars that pulse regularly, getting brighter and dimmer in a predictable cycle over periods that range from a few days to multiple months. She noticed a remarkable pattern in her data. The longer the period of the pulse, the brighter the star actually was intrinsically. This meant that astronomers could measure the period of pulsation, figure out the true brightness of the star based on that period, and compare that intrinsic brightness with how bright the star looked from Earth. Since objects that are far away appear fainter than nearby objects, they could use that comparison to measure the distance to any Cepheid variable star. It was like having a cosmic ruler, a standard candle for measuring distances across the universe. Armed with this powerful new method, Edwin Hubble turned his telescope to the Andromeda Nebula and saw one of these special Cepheid variable stars twinkling within it. He measured the period of its pulsation and calculated the distance to Andromeda using Leavitt's relationship. His result was shocking: 900,000 light-years, well beyond the outer reaches of our Milky Way galaxy. Those island universes that Kant had speculated about actually exist. All of these fuzzy nebulae that astronomers had been looking at for centuries were actually entire galaxies of their own, just like our Milky Way, each containing billions of stars. In that single instant, the known universe as we understood it increased in size by 1,000,000 times. Hubble had changed astronomy forever, revealing a cosmos far vaster than anyone had imagined. Another astronomer named Vesto Slipher had also been looking at these distant galaxies when he noticed something peculiar too. Most of them had their light redshifted, meaning the wavelengths of light were stretched out toward the red end of the spectrum. This indicated that they were moving away from us at insane speeds, hundreds of kilometers per second. We now know that this redshift was caused by the Doppler effect, the same phenomenon that makes an ambulance siren sound different as it approaches and then moves away from you. Building on this foundation, Hubble used his new methods combining insights from both Slipher and Leavitt to measure the distance to a large number of galaxies and figure out how quickly they were moving away from us. He carefully put all of this data onto a plot with distance on one axis and velocity on the other, and the trend was crystal clear. The farther away the galaxies were from us, the quicker on average they were flying away from us. This is exactly what we would expect to see if the universe itself was expanding, with space stretching between galaxies like dots on an inflating balloon. The static universe of Newton, and even Einstein, was dead, killed by observational evidence. Hubble's observations had confirmed what other physicists had actually believed for a while now based on the mathematics. Alexander Friedmann and Georges Lemaitre had been using Einstein's equations of general relativity to predict a dynamic universe, one that changes over time, and they were right. Einstein's cosmological constant wasn't needed after all. They immediately thought to turn back the clock and see what this meant. If the universe is expanding as time passes forward, when we move back in time, it should contract, getting closer and closer together until it reaches an extremely dense and hot state. Lemaitre poetically called it the primeval atom. He claimed that we were living in the smoke and ashes of a bright but very rapid fireworks display. Lemaitre became known as the father of this new theory of cosmic origins, somewhat ironically, because he was also a Catholic priest. Here was a man of faith describing what would become the scientific explanation for the origin of the universe. Remember earlier how we established that space and time are innately linked? They form one singular entity, spacetime. This meant the beginning of space would also necessarily be the beginning of time itself. Time and space came into existence together. Stephen Hawking and Roger Penrose would later go on to show that this wasn't just a convenient assumption either. Time really did stop at this initial dense state. It wasn't just that we couldn't see past it or that our equations broke down. Time itself had a beginning. They did this by taking Penrose's mathematical solutions for a black hole singularity, where there's infinite density and curvature at a single point, and cleverly applied it to the entire universe as a whole. They were able to show, under a specific set of assumptions that seemed reasonable at the time, that the expanding universe we see today had to have started with a singularity in the distant past. A day without yesterday, as Lemaitre called it, a moment before which there was no before. This is probably what you were taught in school, that the Big Bang started from an infinitely dense, infinitely hot singularity. But as we'll see, this is almost certainly not true. The singularity is likely just a mathematical artifact, not physical reality. There was a significant problem with this primeval atom model of the universe that threatened to undermine the entire theory. If you took the observed rate of the universe's expansion and just turned back the clock like rewinding a movie, you could figure out how old the universe was by calculating when everything would have been in the same place. And when they did this calculation, the answer was an embarrassingly young 1.8 billion years old. But geologists at the time already knew from radioactive dating that the Earth itself was at least 4.5 billion years old. How could the Earth be older than the universe? Something had to be seriously off with the theory or the measurements. But to be honest, even without this age problem, Einstein just didn't like the idea of an expanding universe at all. He had deep-rooted philosophical beliefs in his idea of a static, eternal universe, and so he began exploring a new theory that attempted to combine the primeval atom idea with his beloved static universe. If the density of energy in the universe has to remain constant over time, he suggested that new particles of matter should be continually formed to replace matter that spreads out. He imagined a universe expanding without any specific origin point, where the new particles could be created out of nothing, arising from his cosmological constant, the energy of empty space itself. The expansion of space spreads out the existing matter, diluting it, and so new matter is created to keep the total energy density of the universe perfectly constant. Everything would be elegantly solved, and the universe could be both expanding and eternal. But he couldn't get this idea to quite work in the details though. There were all of these small mathematical problems and inconsistencies that he couldn't resolve, and so he didn't publish it or tell anyone about it. The idea was only discovered in his personal archives in 2014, long after his death. Lucky for him though, 3 scientists in England had all thought of the same idea independently all the way back in 1945. Fred Hoyle, Thomas Gold, and Hermann Bondi thought up the same basic concept Einstein had abandoned. They developed it further and called it the steady-state model of the universe. These were the 2 big competing ideas at the time: the primeval atom theory and the steady-state model. Hoyle actually had a popular radio show where he spoke about science to the general public in England, and one time he was on air describing the 2 competing theories when he referred to the primeval atom model dismissively, saying all the matter in the universe was created in one Big Bang at a particular time in the remote past. He meant it somewhat mockingly, but the Big Bang name was born from that moment, and it stuck. Sometimes the best names come from critics. We now had the foundations of the Big Bang theory in place, and it probably sounds pretty similar to what you think the Big Bang actually is. A long time ago, everything in the universe was much closer together and much hotter than it is today, and then bang, the universe began expanding. But there was still much testing to do, many predictions to verify or falsify. One thing that physicists were thinking deeply about is what happens to all of the matter, the planets, humans, stars, galaxies, all of that stuff, as they get traced back in time toward the Big Bang. The physicists George Gamow and Ralph Alpher showed mathematically that as the universe contracts back in time, it would get progressively hotter and denser, and eventually all the complex matter we see today would break down into a primordial soup of fundamental particles: protons, neutrons, electrons, and photons of light. So right after the Big Bang, everything in the entire universe was just this incredibly hot, dense soup of particles. There was no empty space anywhere. Everything was pressed together, It was so unimaginably hot that the whole universe was basically just one gigantic nuclear reactor. The temperature and pressure were so extreme that nuclear fusion could occur everywhere at once. The protons and neutrons would snap together through nuclear forces, forming and combining to create the nuclei of the lightest elements: hydrogen, helium, and lithium atoms. After about 5 minutes of this cosmic nuclear fusion, everything had cooled down enough for this universal nuclear reactor to shut down. All of the atomic nuclei had been formed and locked into their exact proportions, frozen in place. No more fusion could occur. Gamma and Alpha made a specific, testable prediction. They calculated that 75% of the nuclei in the universe should be hydrogen, 25% should be helium, and a tiny proportion of things like lithium would be found. This wasn't a vague guess. It was a precise mathematical prediction based on the physics of nuclear fusion in the early universe. Amazingly, when astronomers looked out at the universe and measured the abundance of these elements, they were right. Observations agreed with this exact ratio. The universe really is about 75% hydrogen and 25% helium, just as predicted. This was powerful evidence that the Big Bang really happened. But they didn't stop there. This team kept thinking carefully about the early universe and their primordial soup. 5 minutes after the Big Bang, after the initial fusion had ceased, the soup was filled with basically 3 things: atomic nuclei, free electrons floating around, and photons of light that had been created in the intense heat of the Big Bang. This light was continually being absorbed by the nuclei and electrons, and then re-emitted, scattering and bouncing around, flying chaotically through the plasma because everything was so hot and dense. The photons couldn't travel very far before hitting something else. The universe was opaque, like being inside a thick fog. The soup would stay in this opaque state for an incredibly long time, about 380,000 years, until it had finally cooled down to a relatively pleasant 2,700 degrees Celsius. In that crucial moment, everything changed dramatically. Immediately, the free electrons snapped onto the closest atomic nuclei, forming the first complete atoms. And with no more free electrons to scatter off of, those photons of light were finally free to fly out through empty space unimpeded. The universe became transparent for the first time. If you were somehow there watching this moment, it would have appeared as a bright red glow filling all of space in every direction. And ever since then, this light should have been traveling out through the universe, being stretched by the expansion of spacetime as the universe continues to expand. The wavelengths get redshifted so much that it should now be in the microwave end of the electromagnetic spectrum, and the temperature should have cooled down to extremely cold, around 2 Kelvin, just barely above absolute zero. They called it the cosmic microwave background radiation, or CMB for short. And they realized that if they wanted to once and for all prove that the Big Bang model was real and not just mathematical speculation, they would need to find this ancient light still traveling through space. And if they could successfully detect it, they would literally be taking a picture of the Big Bang itself, seeing the universe as it was 380,000 years after its birth. The hunt was on, and it became one of the most important quests in all of cosmology. By the 1940s, an astronomer named Andrew McKellar was studying clouds of alcohol molecules in interstellar space when he measured the temperature of that empty space around the clouds. He found it to be about 2.3 degrees Kelvin, surprisingly warm compared to what you'd expect. So what was heating up empty space? Well, he didn't know at the time, and crucially, no one connected the dots between his measurement and the prediction of the cosmic microwave background. He was actually measuring the afterglow of the Big Bang itself and didn't even realize it. The discovery was right there, but the connection wasn't made. In the meantime, the steady-state model was basically dead, killed by accumulating evidence. The main problem holding back the Big Bang model was this age problem. It predicted the universe was far too young. But then new, more careful data showed that the original distance calculation to the Andromeda galaxy had been miscalculated due to confusion between different types of variable stars. It was actually over 2.5 million light-years away, much farther than Hubble originally thought. So using this corrected data and recalculating, the age of the universe was now predicted to be somewhere between 10 to 20 billion years old, plenty old enough for the Earth to have formed. The age problem was solved, and another objection to the Big Bang evaporated. Astronomers at Princeton had set their sights on detecting the CMB, and they were getting tantalizingly close. They could feel they were on the verge of a major discovery, but someone beat them to it. Just down the street at Bell Telephone Laboratories, 2 radio astronomers named Arno Penzias and Robert Wilson had been working with a large horn antenna designed for satellite communications. They had detected this strange, persistent hiss in their data that they couldn't explain or eliminate. They tried absolutely everything to remove it, but to no avail. They even cleaned out pigeon droppings from the antenna, thinking that might be the source, but the signal remained. That's when they spoke with some theoretical physicists from nearby MIT, and they suddenly realized what they were looking at. It was in fact the cosmic microwave background radiation that had been predicted, measured at almost exactly 2.7 degrees Kelvin, precisely what the theory predicted. They had accidentally stumbled upon one of the most important discoveries in the history of science. Penzias and Wilson received the Nobel Prize for this discovery, and the Big Bang Theory had its crown jewel piece of evidence. This wasn't just indirect support, this was direct detection of light from the early universe itself. If we could see the CMB with our eyes today, as it was when it was first emitted 380,000 years after the Big Bang, and take a picture of it, it would look like a red glow filling the entire sky coming from every single direction you look. The light from the Big Bang itself, still traveling through space after nearly 14 billion years. And it wasn't long until they did just that, took a detailed picture of it across the entire sky. By 1982, NASA had approved the creation of a spacecraft specifically designed to image the entire cosmic microwave background with unprecedented precision. It could sweep across the sky systematically, mapping what the CMB looked like in every direction with great sensitivity. The satellite was called COBE, the Cosmic Background Explorer, and by 1990, after years of careful observations and data collection, they had all the data they needed and made their big public reveal to the scientific community and the world. The CMB in all of its glory mapped across the entire celestial sphere. They had mapped the entire sky's contribution to the microwave background and produced the most complete and detailed image of the CMB ever taken. Stephen Hawking declared the result the scientific discovery of the century, if not of all time. Scientists around the world celebrated. And it wasn't just beautiful to look at. It confirmed something fundamental that scientists had suspected for decades, but couldn't prove. In physics, there's something called a black body. It's an idealized object that absorbs absolutely all light that hits it, 100% of it, without reflecting anything. All of that absorbed energy should then be re-emitted by the object in a perfectly predictable way based purely on its temperature. Its light spectrum should have a very specific mathematical shape. Depending on the temperature of the object, this spectral shape could shift, but there is always a perfect theoretical spectrum shape for any black body at a given temperature. The physicists had predicted that the CMB should have this precise signature of a perfect black body spectrum, and when they measured it with COBE, it did. Not approximately, but exactly. It was the most perfect black body spectrum ever observed in the history of physics. The data points matched the theoretical curve so perfectly that you couldn't even see the difference. This was stunning confirmation that the CMB really was thermal radiation from the hot, dense early universe. Standing ovations at conferences, Nobel Prizes awarded, and what seemed like an accurate and complete description of how the universe was born. So that's the end of the story, right? The universe started with a bang from a singularity, and that's it. We understand cosmic origins now. Well, not quite. Not even close, actually. There were three huge, fundamental problems that were still left completely unanswered by the standard Big Bang model. Problems so severe that they threatened to undermine the entire theory. The first major problem is known as the horizon problem, and it's subtle but devastating. We have since mapped the CMB to extremely high precision using better satellites, and measured the thermal temperature difference across the entire sky with incredible accuracy. And what we find is that it's nearly perfectly uniform. The entire CMB signal is pretty much exactly 2.7 degrees Kelvin, no matter where you look in the sky. The temperature variation from one side of the universe to the other is less than 1 part in 100,000. It's incredibly smooth and uniform. The problem is this: there was nowhere near enough time for the temperature to equilibrate from one side of the universe to the other and let everything come to such a perfectly even temperature. For two regions to reach the same temperature, they need to be in thermal contact. Heat or light needs to travel between them. Even traveling at the absolute speed limit of the universe, the speed of light, there was no possible way that 2 points in the CMB from opposite sides of the observable universe could have thermalized and reached the same temperature in the mere 380,000 years before the CMB light was emitted. The regions are simply too far apart. It would have literally taken trillions of years for light to travel between them, but the universe was less than 500,000 years old. And you might think that maybe the problem would be solved if the universe were just perfectly uniform right from the very start, with everything at exactly the same temperature from the beginning. But if that were the case, if everything were perfectly smooth, we wouldn't see the abstract, clumpy distribution of galaxies we observe today. We need some variation, some lumpiness, but not too much. The universe appears fine-tuned in a way that seems to require explanation. The second major problem is known as the flatness problem, and it's equally mysterious. Space in the universe can have different geometric degrees of curvature, different shapes. The amount of curvature is mathematically given by a number called omega. If omega equals exactly 1, then space is perfectly flat, and parallel lines will stay parallel forever, never meeting. If omega is less than 1, space is negatively curved like a saddle, and parallel lines will diverge apart from each other, spreading out. And if omega is greater than 1, space is positively curved like the surface of a sphere, and those very same parallel lines will eventually converge and meet. When we actually measure the curvature of space in real life using multiple different methods, we find it's nearly perfectly flat to within measurement error. But here's the thing: This prediction of a flat, expanding space is inherently really unstable from a mathematical perspective. If there's any slight deviation from omega equals 1 in either direction, even by a tiny amount, it would rapidly diverge away from that value as the universe evolves, like a pencil perfectly balanced on its tip, inevitably falling over. The flat solution is what mathematicians call an unstable equilibrium point. And since we measure omega as essentially 1 today, after nearly 14 billion years of cosmic evolution, it must have been unimaginably, impossibly close to exactly 1 in the distant past. We're talking about fine-tuning to dozens of decimal places. If omega wasn't so incredibly close to 1 in the early universe, the consequences would be catastrophic. If it were too large, the universe could have collapsed almost immediately. If it were too small, it would have expanded so rapidly that no structures could ever form. The universe could tear itself apart or collapse and destroy itself almost instantly. So why is the universe so incredibly, precisely flat? What mechanism set it to such an exact value? The third major problem is known as the monopole problem, and it was pointed out by particle physicists studying the early universe. At such incredibly high energies like those that would have been present in the earliest moments of the universe, a huge number of these strange, exotic particles called magnetic monopoles should have been inevitably formed according to our best theories of particle physics. These are hypothetical isolated magnets with just one magnetic polarity, either a north pole or south pole, with no corresponding opposite pole. They're like breaking a bar magnet in half and getting just a north pole with no south pole attached. The problem is that despite extensive searches, we have never found even a single magnetic monopole anywhere in the universe, and according to the theory, they should have been produced in enormous quantities, and they would have been incredibly massive particles, so heavy that they would have dominated the mass energy of the universe and prevented the universe from expanding at all, or at least slowed it down dramatically. The universe should be full of these things, but we see exactly zero. Where did they all go? And beyond these three specific problems, there was still the elephant in the room, the singularity itself. Most physicists felt deeply uncomfortable with it, sensing that something had to be off, that the singularity was just an artifact of pushing the mathematics too far beyond where it's valid. Singularities in physics usually indicate that your theory has broken down, not that nature actually becomes infinite. Einstein himself called the idea that the universe actually started at a Big Bang singularity repugnant to his physical intuition. It just didn't feel right. By this point in our story, everything had started to come to a head. The Big Bang model worked incredibly well to explain much of what we see, but these problems suggested something important was missing. Hawking and Penrose's celebrated mathematical proof of the singularity hinged critically on 4 key assumptions. First, that gravity is always attractive and never repulsive. Second, that the universe has exactly 3 space dimensions and 1 time dimension. Third, that time travel into the past is physically impossible. And fourth, that Einstein's theory of general relativity accurately describes the evolution of the universe at all scales, even at the very beginning. And now, decades later, every single one of these assumptions is in serious doubt, especially that fourth one. We know that general relativity has some very big problems when it comes to quantum scale interactions, where it fundamentally disagrees with quantum mechanics. At the incredibly tiny scales and enormous energies present in the earliest universe, quantum effects should dominate, and GR might not apply at all. Both Hawking and Penrose themselves have since disavowed many of these assumptions in their later work. Their famous singularity proof that time started at the Big Bang had fallen apart under scrutiny. It's clear that we needed something more, something better and more complete than just the Big Bang singularity as a theory of cosmic origins. Our solution would come from a brilliant physicist named Alan Guth working at MIT. Guth was thinking deeply about phase transitions in ordinary physics and how they might apply to the early universe. Think about ice cubes turning into liquid water as they melt when you heat them up. If you then heat the liquid water more, you get steam, water vapor. These are phase transitions, where matter changes from one state to another. But there are some strange kinds of phase transitions, too, that don't happen instantly. If liquid water is pure enough and undisturbed, it can actually be cooled down below the normal freezing point of 0 degrees Celsius without freezing, delaying the phase transition in a process known as supercooling. The water wants to freeze but needs a nucleation site, a tiny imperfection or disturbance to trigger the transition. You can supercool water to several degrees below freezing, and it will remain liquid until something triggers the sudden transition to ice. In the Big Bang model, it was thought that the universe cooled down from an effectively infinite temperature as it rapidly expanded, going through various phase transitions along the way. But this standard cooling process would inevitably give us the monopole problem. Those magnetic monopoles would form in huge quantities. So what if the universe could be supercooled, delaying the phase transition like we can with water? Guth and others calculated that if the cooling is delayed through supercooling, if the phase transition happens later than expected, the monopole problem simply disappears. The monopoles just don't get created in the first place, because the conditions for their formation never occur. The question then becomes crucial. What does this supercooling do to the expansion rate of the universe? Does it change how fast space expands? Well, you might normally think of empty space as, well, what it sounds like intuitively, just completely empty, a void, nothing there at all. But quantum mechanics has shown us something profoundly strange. Empty space really is a seething sea of chaotic quantum activity happening at scales far too small for us to see directly. Hidden from our everyday perception, there's an underlying layer of quantum fields permeating all of space, each one corresponding to a specific type of particle. There's an electron field, a quark field, a photon field, and so on for every particle we know of. When there's a ripple or excitation in that particular field, we observe and detect the particles that make up you and me and everything around us. Our electrons literally come from ripples in this underlying electron field that fills the universe. In this seemingly empty space, quantum mechanics tells us that particles and antiparticles like electrons and positrons pop in and out of existence all the time, constantly. They're created in pairs out of nothing, briefly moving apart and existing for a fleeting instant before reuniting and annihilating each other, disappearing back into the vacuum of the quantum fields. These are called virtual particles. It's these weird quantum interactions and fluctuations that give the vacuum of empty space a tiny little bit of energy density. It's not truly empty, it has a quantum energy associated with it. And remember Einstein's famous equation: energy and mass are equivalent, just different forms of the same thing. So if you have enough empty space with its vacuum energy and can somehow extract that energy from the vacuum, you can get enough mass energy to create substantial things, particles, atoms, even potentially the entire universe worth of matter and energy. This sounds crazy, but it's a prediction of quantum field theory. Guth started to carefully calculate how quickly the universe would expand if it were driven primarily by the energy of this quantum vacuum of space, rather than by matter and radiation. And the expansion rate was absolutely insane, far faster than normal expansion. The universe, in a tiny fraction of a second, in an almost incomprehensibly short time, would expand exponentially by at least 100 trillion times, maybe much more. The numbers were staggering. He immediately realized that this insane period of exponential growth, this burst of rapid expansion, would immediately fix the flatness problem in an elegant way. By using this period of incredibly rapid growth driven by vacuum energy, the equations governing the universe's curvature got flipped upside down. The flatness wasn't unstable anymore. Instead, the value of omega, representing the curvature of the universe, was rapidly driven toward exactly 1 during this exponential expansion phase. No matter what shape or curvature the universe was initially in, no matter how curved it started out, the vacuum energy-driven exponential expansion would perfectly flatten out the universe, smoothing it like stretching a wrinkled sheet. The flatness problem was completely solved, and it didn't require any fine-tuning at all. When Guth did this calculation late one night, he knew immediately he was onto something revolutionary and big. He wrote in his notebook, "Spectacular realization. This kind of supercooling can explain why the universe today is so incredibly flat, and therefore resolve the fine-tuning paradox. The problem that had plagued cosmologists for decades seemed to disappear like magic, all thanks to this brief period of exponential rapid expansion in the earliest moments." Guth named this new phase of cosmic evolution inflation. The universe underwent a period of inflation before the hot Big Bang we learned about in school. The final problem inflation had to solve was the horizon problem, and it turned out to be actually quite simple and elegant. Since inflation grew the size of the universe by such a huge, enormous amount in way less than a fraction of a second, any 2 points that we see today in the CMB that appear too far apart to have ever been in thermal contact, too far apart to be able to communicate and come to the same temperature in the old model, would have actually started out much closer together before inflation began. They were initially in a tiny region small enough to be in thermal contact. This gives them plenty of time for the photons to go back and forth, for heat to flow between regions, and arrive at exactly the same temperature through normal thermal processes. Then inflation rapidly blows up this small, thermalized region to cosmic scales, preserving that uniformity. That's why the CMB looks so incredibly uniform today across the entire sky, even though different regions seem like they should never have been able to communicate. They were in contact before inflation, reached thermal equilibrium, and then were stretched apart. The horizon problem was elegantly solved too. This theory of inflation was performing what seemed like magic tricks. It solved all 3 of the most pressing, fundamental problems for the Big Bang theory just like that, in one elegant stroke, while simultaneously replacing the problematic pesky singularity in the process with something more physically reasonable. And that wasn't even its biggest triumph or most important prediction. When we look out at the cosmic microwave background with our most sensitive instruments, we can see these subtle areas that have a slightly higher density than average. There's a little bit more of that primordial soup, slightly more energy, concentrated here than in those slightly colder spots over there. The variations are tiny, only about 1 part in 100,000, but they're crucial. And since gravity always pulls more matter toward these slightly overdense regions, attracting more and more material over time, these little tiny variations explode and grow over billions of years, thanks to the relentless pull of gravity, giving us the cosmic web of galaxies and large-scale structure that we see in the universe today. If the CMB were perfectly, absolutely uniform with no variations at all, with every point at exactly the same density, the universe would have no galaxies at all, no stars, no planets, no structure whatsoever. Everything would be spread out perfectly evenly forever. We wouldn't exist. But if the variations were too large, too pronounced, everything would have collapsed into black holes almost immediately. The universe is balanced on a knife edge. Inflation is driven and powered by the quantum inflation field, and quantum fields have built-in inherent quantum fluctuations thanks to Heisenberg's uncertainty principle. At the quantum level, everything fluctuates randomly. These quantum fluctuations in the inflation field get stretched out by the exponential expansion, and then frozen into the plasma as the expansion eventually slows down and inflation ends, giving us the small density variations that we see today imprinted in the CMB. If it weren't for these quantum fluctuations during the inflation period, there would be no galaxies, no structure in the universe today, and we wouldn't be here to observe it. Inflation naturally produces the seeds of all cosmic structure. Combining all of these ideas together, the quantum fields, the vacuum energy, the exponential expansion, the phase transition, we can finally piece together a complete, coherent view of what actually banged during the Big Bang. What was it? Here's the modern picture. We start with empty space, a tiny patch of space smaller than a grain of rice, maybe even smaller than an atom. There's no matter or light in it, nothing at all that we would recognize. But our empty space is filled with an underlying quantum field, the inflationary field, permeating it. This field has a very special property. It has a large amount of vacuum energy associated with it. And this field forces that tiny patch of empty space to rapidly, exponentially increase in size, driven by its own energy density. If that initial patch started out to be around the size of a grain of rice or smaller, it would have grown through exponential expansion to be bigger than our entire observable universe is today in less than a trillionth of a trillionth of a trillionth of a single second. The numbers are so extreme they're hard to even comprehend. Space itself expanded faster than light, which is allowed because nothing physical is moving, it's space itself stretching. Keep in mind, at this point in the process, there is still absolutely nothing physical in this space. No particles, no atoms, no light, no matter. Just empty space filled with the inflation field's vacuum energy, expanding exponentially. The universe is cold, dark, empty, but growing at an incomprehensible rate. And then suddenly, inflation ends. The inflation field undergoes its delayed phase transition, finally decaying out of its high-energy state. And bang, just like that in a moment, all of the enormous energy stored in this inflationary field of empty space, all that vacuum energy that was driving the expansion, gets immediately converted into real matter and real radiation, into actual particles and light in the universe. This is the hot, dense Big Bang that you were taught about in school, the fireball that everyone pictures. The light we see is the CMB today, and all the matter that forms every single star, every planet, every galaxy, every atom in your body. All of it is formed from the vacuum energy of the inflation field in that moment of decay. The universe goes from cold and empty to unimaginably hot and dense in an instant. No need for any singularity at all. No infinite density, no infinitely small point, none of that. Just a quantum field undergoing a phase transition and releasing its energy. The singularity, that troublesome concept that physicists found so repugnant, is replaced by something more physically reasonable. A quantum field in a temporary high-energy state. The math doesn't break down. Physics still works. But here is the absolutely crazy part about inflation, the part that has profound philosophical implications. Inflation doesn't end everywhere all at once throughout space. It happens in patches, in different regions at different times, in a random, probabilistic way driven by quantum mechanics. So while inflation might decay into matter and radiation in one region, creating our universe and our Big Bang right here, right where we are, it can continue inflating exponentially forever outside of our patch, in the regions beyond what we can see. And in these eternally inflating regions, new patches will randomly decay and undergo their own phase transitions, spawning potentially infinite numbers of these Big Bang universes, these pocket universes as they're called, each one potentially with different properties, different physical constants, maybe even different laws of physics. And we just happen to be inside one of these pocket universes, one of these patches. There's an eternally inflating multiverse out there, constantly spawning new Big Bang universes forever. The multiverse is born from the mathematics of inflation, whether we like it or not. And that right there's the most widely accepted view among cosmologists of how our universe came to be. It's probably not at all what you were taught in school, is it? Even in university physics courses, it's often taught incorrectly or incompletely. Inflation happened before the Big Bang, not after it. The Big Bang wasn't the beginning, it was the end of inflation in our patch of space. the singularity probably isn't real, and there might be countless other universes beyond our own. So case closed, right? End of story. We've figured out cosmic origins completely. Well, not quite, not by a long shot. As you've seen throughout this entire story, the field of cosmology is constantly evolving, constantly changing, and new theories and ideas are always popping up, claiming to have a better, more accurate, more complete description of the origin of the universe and what came before. While this theory of the inflationary Big Bang is currently the best we have, the leading paradigm accepted by most cosmologists, it doesn't come without its own serious problems and criticisms. Some popular and respected critics argue that inflation is just too flexible, too adaptable, and not falsifiable enough to really be good science. The theory has so many possible variations and free parameters that it can be adjusted to fit almost any observation. In science, a good theory doesn't just explain what we see, it has to make specific, risky predictions that could be proven wrong. A scientific theory has to make clear, testable predictions that can be verified or falsified using observations from our telescopes, satellites, and detectors. And while inflation does make some predictions that have been confirmed, like the pattern of density fluctuations in the CMB, critics argue it's become too malleable. You can always adjust the details of the inflation model to match whatever we observe. But inflation also predicts this eternal multiverse, this infinite collection of pocket universes, and that's something physicists aren't very comfortable with at all. How do you test a theory that predicts the existence of regions of space we can never, even in principle, observe or interact with? How do you do science about the unobservable? The multiverse prediction troubles many physicists because it seems to take us outside the realm of testable science and into philosophy or metaphysics. And before you go rushing to the comments section saying, see, physicists can't even agree on what the Big Bang actually is or how it worked, so how are we expected to believe any of it? It's all just speculation and guesswork. Slow down for a moment. There are things that we know for a fact, with absolute certainty, to definitely be true based on overwhelming observational evidence. The hot, dense Big Bang, just meaning that everything in the universe used to be really close together, compressed into a much smaller space, and much hotter than it is today, definitely, unquestionably happened. We can literally see it with our telescopes. We see the cosmic microwave background radiation. We measure the abundances of light elements. We observe the expansion of the universe. That is not speculation. That is not up for debate among scientists. The evidence is overwhelming and conclusive. But looking beyond that well-established hot, dense state, and trying to answer deeper questions of what caused that hot, dense state, what mechanism created it, and what came before it, if anything, that's what's still undecided and actively debated. That's the frontier of research. The hot Big Bang is established fact. What caused it is the open question. When leading physicists at the cutting edge of this field, people working on quantum gravity and the very early universe, were surveyed about what they believed to be true about the beginning of the universe and the nature of the Big Bang, the results were fascinating. When they were asked directly if they believed that the Big Bang was the absolute beginning of time, that nothing came before it, the majority of them actually disagreed. Most said the Big Bang, as we understand it, says nothing definitive about when time in our universe truly began, or whether something preceded it. Alan Guth himself, the father of this entire inflation idea, the person who started this revolution, said something very important. The Big Bang theory was never actually a theory of the bang itself. It says absolutely nothing about what banged, why it banged, how it banged, or what happened before it banged, if anything. It's a theory of the aftermath of what happened after. And that's probably a good, honest way to think about this description of the Big Bang. The Big Bang theory describes the evolution and expansion of the universe from a hot, dense state. It does that remarkably well. But it doesn't claim to explain the ultimate origin of that state. Inflation is our best current attempt to explain what created the hot Big Bang, but even inflation might have a deeper cause or might be part of a larger picture we don't yet understand. There are other competing ideas too, alternatives to inflation that try to solve the same problems. Some physicists are working on models involving quantum gravity effects, others on cyclic models, where the universe goes through infinite cycles of expansion and contraction, and still others on ideas involving extra dimensions or modifications to general relativity. The truth is, we don't know for certain yet. What we do know is that the universe is expanding. It was once much hotter and denser, and the evidence for this is rock solid. Everything beyond that, the inflation, the multiverse, what came before, is our best current attempt to understand the ultimate origins, but it's still a work in progress. Science is a process of continually refining our understanding, not a collection of unchanging dogmas. The universe doesn't owe us the courtesy of being easily understandable, and the fact that reality at its most fundamental level is strange, counterintuitive, and still partially mysterious should fill us with wonder, not doubt. We've come incredibly far from Newton's static eternal universe to Einstein's dynamic spacetime to the modern picture of inflation and the Big Bang. Each step revealed a cosmos more vast, more ancient, and more strange than we imagined. And the journey of discovery continues. New telescopes are being built, new satellites launched, new theories developed and tested. The James Webb Space Telescope is looking back to the earliest galaxies. Gravitational wave detectors might someday see ripples from inflation itself. Particle accelerators are probing the physics of the early universe. We're living in a golden age of cosmology. The question of how the universe began, what happened at the very beginning if there was a beginning, is perhaps the deepest question humans have ever asked. And while we don't have all the answers yet, we've made remarkable progress. We've gone from mythology and speculation to precision measurements and mathematical theories. We've seen the afterglow of creation itself. So the next time someone asks you what the Big Bang was, you can tell them it's not what they taught you in school. It's not an explosion in space, but the expansion of space itself. It's not necessarily the beginning of time, but possibly the end of an earlier phase called inflation. It's not a singularity we're sure about, but perhaps a quantum field transition. And it might not be the only one. There might be countless other Big Bangs in an eternal multiverse. The Big Bang is both more certain and more mysterious than most people realize. More certain because the evidence for the hot, dense early universe is overwhelming. More mysterious because the ultimate origin and cause of that state remains an open, fascinating question at the very frontier of human knowledge. And that's exactly where science should be, not claiming to have all the answers, but honestly pursuing them, following the evidence wherever it leads, and remaining humble in the face of the cosmos. The universe is under no obligation to make sense to us, but remarkably, slowly, piece by piece, we're figuring it out. And that's perhaps the most amazing thing of all.